So this chapter is chapter 10, acid bases, and equilibrium. We're going to start with the generic properties of acids. Acids, as you know, hydrochloric acid as an example, has a sour taste. You may think of that as citric acid having a sour taste, or vinegar, acetic acid, having that sour taste. It can dissolve many metals. You've seen this in your reactions lab where we've taken a metal, dissolving that in an acid, and it will turn litmus paper red. Litmus paper, you may have heard of something called a litmus test, and it's like a quick yes or no test for something. Litmus paper will turn red in the presence of an acid. The bases are kind of the opposite of acids, and so bases have a bitter taste. They have a slippery feel, and so you can think of them like soap is a base, and then they will turn litmus paper blue. Caffeine is an example of a base. We have a few different definitions of acids and bases, and the first definition is called the Arrhenius definition. Arrhenius definition is kind of just what an acid is in its formula. And so an Arrhenius definition says that acids make H+. And so if you remember chapter 6, when we write and name acids, we assume that all acids have H+ in them. Acids will release H+ into water. And then when those H+, those hydrogen ions bond with water to form hydronium. And so you need to know something about hydronium. Is that H+ is equal to hydronium in water. So as soon as you have water hanging out, so if you look here is the Lewis structure for water, and this is the dots that I don't like. So if you wanted to kind of think about water not with the dots, we can draw it like this. So if you have an H+, the negative side of this oxygen is going to bond with this H+, creating a hydronium, which would look like this. And it would get a plus charge since we're adding this H+ to our water. And this just automatically happens in water. So you can never have a hydrogen ion actually in water present as only a hydrogen ion, because as soon as it shows up, that water is going to snatch it up and make a hydronium. Then we have a base. A base typically has hydroxide, and so you're seeing an Arrhenius base here as sodium hydroxide. You have a list of strong acids and bases to memorize, and you can see that most of your strong bases are hydroxides. So Arrhenius acids and bases will react together to make water, and you may have seen some of these in your lab. You've got the H+ from an acid, you've got the OH from a base, and together they neutralize into water. So you can even rewrite water sometimes as HOH to help you balance it, but then make sure you always turn it back into H2O. So some characteristics of acids and bases. They are electrolytes because they produce ions, and so that's something of course to make note of. And then you will do a lab with this thing called phenolphthalein, and it will change color in the presence of a base. And then they neutralize each other. So if you have a base and you want it to go away, you neutralize it with an acid. And so if you've ever seen me clean up a spill in the lab, I will always pour a base on an acid and an acid on a base in order to neutralize it before I dispose of it. So the definition that we're going to really focus on in this course is the Bronsted-Lowry definition of acids and bases. So Arrhenius is okay, but it doesn't include all of the acids and bases that we're going to see. Typically, ammonia, NH3, is a base, but it's not by Arrhenius definition. And so Bronsted-Lowry definition is a much better definition because it gives us what the acid and the base is doing, a deeper understanding, not just what does it look like. And so I want you to know that a Bronsted-Lowry acid is a proton donor and a Bronsted-Lowry base is a proton acceptor. What do I mean by proton? Well, a proton is just P+, right? It's a proton. What am I talking about? Proton. I don't see protons, no P+ here. I see this H+. And so you see this H+ donation. Let's think about hydrogen. So if we draw the the Bohr model for hydrogen, look at the periodic table. How many protons go in the nucleus? Well, in hydrogen, there's one proton. How many electrons are hanging out? So in hydrogen atom, you have one electron in the first energy level because it's 1s1. If you make a hydrogen ion, a cation, are you gaining or losing electrons? right? You are losing electrons. So if I only have one electron and I lose that electron, I only have one proton in the center, so I would be 1s, 0. It's just a proton. So a hydrogen atom is equal to a proton. So when the definition says proton donor, it means H plus donor. Proton acceptor means H plus acceptor. And so looking at this reaction here, we see, and we'll do a quick little tracking of this, we have our hydrogen chloride or hydrochloric acid in water that makes hydronium and chloride ion. So let's track this H here. We see that this hydrogen is being donated to the water. So when water takes a hydrogen, it becomes H3O plus because it's taking the H and the plus. What's left over would be Cl minus, the chloride. And so you can track it and get a definition. If the H is going away from the substance, it's an acid. So H away, acid. If the substance is accepting the H, so the H is going toward that substance, then it is a base. It is accepting the proton. We can see here ammonia is reacting with water, and notice that it's a double-sided arrow, meaning that it doesn't go very well to the right. It doesn't go all the way. So you remember this from your electrolyte slide. This would be a weak electrolyte. So you can see, let's track what's going on here. So who is accepting the H+? So you see NH3 turns into NH4+. Well, that means the ammonia accepted the H+, and so it's acting as the base. Well, water is giving away the H. So you see H2O turning into just OH-. So it's giving away an H, and it's giving away a positive, making it negative. So water is acting as an acid. Water can act as a base, as we saw in this example, or it can act as an acid, as we see in this example. So why don't you give it a try? So pause and give this a check. So tell me what's the acid and what's the base. We're going to be highlighting a specific hydrogen to look at. And so here, I see that this hydrogen is being donated to the water. And so if this is the donator, this is the acid. And if this is the acceptor, this is the base. And you can tell by looking here, HNO3 turns into NO3. So nitric acid turns into nitrate. If we look here, hydrofluoric acid reacts with water. The hydrogen is being given to the water to make hydronium and the fluoride ion. So this is the acid, and this is the base. Now we have one more definition to look at, conjugates. Conjugates are what's left over after an acid and base does its job. And so looking here, we don't really like to think of strong things as having conjugates because they don't go in the reverse. But you can technically label it if you wanted to try. If you have an acid here, what goes with the acid after it gets rid of its H? The Cl minus. And so the conjugate for this acid would be the Cl minus, but it doesn't have any basic properties, so I'm not going to call it a conjugate base. So even though your textbook sometimes may ask you to identify conjugates for strong things, things that only go one way, I'd like for you to think about them only in context of a reversible reaction. So looking here, if you have ammonia donating an H+, an ammonia taking on an H+, turning into ammonium, and water donating that H+, turning into hydroxide ion, you actually get conjugate acids and bases in the reverse direction. And so we can identify the conjugate by looking at the reaction in reverse. If you look at this reaction and track your hydrogen, so looking at the hydrogen we're going to track one of these hydrogens, I see that there is a hydrogen being donated to the hydroxide to make it water. And it's being donated to the hydroxide, leaving NH3 behind. So this is acting as the acid donating in the reverse direction. And so I call it the conjugate acid. Then this is acting as the base in the reverse direction, so I call it the conjugate base. So to find a conjugate acid and base, it's helpful to reverse your reaction and do the same thing that you did to find the original acid and base. You can also think about it individually without having a chemical reaction. And so if I give you a base and I ask for the conjugate acid that goes with that base, you would do what base does. A base accepts an H+, and so you literally will add one H and one plus to your formula. Versus an acid, the job is to donate or remove H+, so you will literally take away an H and take away a plus from the formula. Here's another example. You can see going from left to right, you have this hydrogen being donated, making bisulfate and hydronium. In reverse, and this should be reversible, in reverse we have the hydrogen being donated from the water, or the hydronium, to make water. And so this is acting as the acid in reverse, so we call it the conjugate acid, versus this acid acting as the base in reverse, so we call it the conjugate base. So do a quick pause and try to write conjugate acids and bases for these. Okay, so coming back, your solutions here. The conjugate base of HBr is Br-. Because HBr is an acid, we must let the acid do its job. To do its job, you subtract an H+. And so for all of these, we'll get rid of one H+. Our answer is going to be highlighted here. You're getting rid of an H, and you have to also change your charge. If you get rid of a positive to a neutral compound, it becomes negative. And so I think about it as just getting rid of an H and getting rid of a plus. For these, if I give you a base, you're going to be adding H+. And so getting rid of adding an H+, you add an H, and then you add a plus, and you get these compounds. Tell me which of these contain acid-base conjugate pairs. So pause and go through it. So is this an acid-base conjugate pair? What you're going to look for is a difference of H+, only one H and one plus. If you were to get rid of H+ for this nitrous acid, would it be nitrite? Yes. This is a conjugate acid-base conjugate pair. If you take this carbonic acid, is the difference in one H and one plus? No, this is not the difference because there's two H's difference here. And so what would be the correct answer for carbonic acid? It would be HCO3- when you get rid of an H+. What about hydrochloric acid and the chlorate ion? Hydrochloric acid, if you get rid of the H, you get Cl-, not chlorate. So that's really important that you have that nomenclature of acids because you will get caught up in a question like this. Now if you have HS-, this is acting as a base. And so HS- is acting as a base. If you add an H+, does it become two H's and an S? Yes. And here, the NH3, if it acts as a base, would it turn into NH4+? Yes. We'll do one more learning check for me, so pause and try this one. So looking at a reaction, this should actually be reversible, sorry. Let's just identify everything. And so looking at this beginning reaction, we have this H being donated here, so therefore this is the acid, and this is the base. To reverse this reaction, we can follow what's happening here. I have the hydrogen going from here to here, so this is the acid, but it's in reverse, so I'm going to call it the conjugate acid. So this must be the base. And in reverse, I call it the conjugate base. So where are my pairs? The acid pairs with the conjugate base. And the base pairs with the conjugate acid. So you have a different level of strengths of acids and bases. Strength has to do with how well it breaks into ions. So complete ionization would be strong. And we designate that with a single arrow. And so if your arrow is only pointing forward, no reverse, you're strong. So you can think about it like this. The hydrochloric acid is very strong at donating. So it will never accept back. It will only ever donate. And so if you put hydrochloric acid or hydroiodic acid, a strong acid, into water, it 100% turns into hydronium and the ion that it makes. And so strong acids break apart. And we learned this word in chapter 9, dissociate. 100%. So 100% breaks down, none left over. Which makes it a really good electrolyte, right? Because it makes a bunch of ions. And so you have some strong acids that I'd like for you to memorize. I would like for you to know these 6 strong acids. The rest of them are weak. If they're not strong, they're weak, and that's the way you can memorize the weak ones. So what does a weak acid look like? We show it as a back and forth. So hydrofluoric acid will donate its hydrogen ion, but it will also take it back. Most acids are weak acids, and they have very strong conjugate bases. So if you look at this, we think about reactions going in the forward direction, but this reaction actually goes better in the reverse direction. Look at the results here. If you put hydrofluoric acid in water, it stays hydrofluoric acid most of the time, and only about 1% will actually ionize. And so which is the stronger direction? Well, going right, if that were really strong, we would have a lot of hydronium and fluoride, but we don't see that. We actually have a lot of HF. So the reverse direction is actually a stronger reaction. And so this conjugate base here, this fluoride, is way stronger than the hydrofluoric acid is an acid. This is a stronger base than this is an acid. Because it makes a few ions, we consider it a weak electrolyte. So weak acids are weak electrolytes. So again, your weak acids are everything on the bottom here, and you don't really have to memorize them. Just know if it's not strong, it's weak. And here's a list of strong and weak acids and their conjugate bases. And so you can kind of check this conjugate idea of looking at this. So as you get weaker in acid, your base strength gets greater. And so your hydroxide ion is your strongest base because water is your weakest acid because water is neutral. So just a quick comparison side by side, we can see that strong acids 100% make ions. Weak acids 1% make ions. Bases are exactly the same. So strength has to do with how well it breaks apart. If you put sodium hydroxide in water, it 100% breaks apart into sodium and hydroxide ions. Here is a list of strong bases. You have a list of strong bases on your memorization sheet. Weak bases, just like weak acids, go back and forth. And so they're weak electrolytes. We're going to include ammonia in this list. And that's the only one that I really need you to focus on, is ammonia is your weak base. Every other you should memorize your strong bases, and then ammonia and bicarbonate as well. So ammonia and bicarbonate, those are weak bases that you should know. That again is on your handout, so you probably already have that as a flashcard. So go ahead and do a quick check. Alright, so HBr, this is a strong acid. Nitrous acid, it's not strong, so it's weak. Sodium hydroxide, this is a strong base. Sulfuric acid is a strong acid. And copper 2 hydroxide, that is a weak base. Because it is a hydroxide, so it's a base, but it's definitely not one of our strong ones. It doesn't really dissolve in water, so it can't really make ions if it doesn't dissolve. So we're going to talk about acid-base equilibrium. This should be a double-sided arrow here. By first talking about hypoxia. So hypoxia is when you don't get quite enough oxygen to react with the hemoglobin in your body. And so we make hemoglobin attaches the oxygen to make oxyhemoglobin in our blood. And the heme group is actually an iron group that is inside of this big compound in your blood. And the oxygen adheres to that, making oxyhemoglobin. And you can think about this equilibrium as kind of shifting back and forth. And so we kind of go this way, then we go this way, and this way, and this way. So if I don't have enough oxygen, what happens is my body will try to make more oxygen, and it can sometimes cause a rise in hemoglobin in my body without enough oxygen to react. And so that can throw things off. And if you have too much oxygen sometimes, you can make too much oxyhemoglobin. And so we really have to keep a very delicate balance in our bodies of these different things. So what does this arrow mean? This arrow means dynamic equilibrium, and it means two opposing processes occurring at the same rate. So what is equal at equilibrium? The rate. It is not the amount. The rate is equal at equilibrium. Amount of reactant and product does not have to be equal. The amount of reactant and product does not have to be equal. That is not what's equal at equilibrium. It's the rate forward and reverse. So it gets into this groove, forward and reverse, and this groove kind of tells you what the system is doing. So that is equilibrium. Now, we say dynamic because it is constantly changing. So this reaction at equilibrium is still going forward and still going in reverse, but I'm not actually going to see any change occurring. So let's look at some graphs for this to kind of help us get this idea. So two things that are true in equilibrium, and this is a great multiple choice question. There are no changes in the concentration of reactants and products. The reaction is still happening, but the amount of reactants and products has stayed the same. And the rate of the forward is equal to the rate of the reverse. And so looking at this graph, as the reaction goes forward in time, the concentration of reactants and products. So if we start in the reaction, the products are 0. And then as we make products, it increases. And as we start the reaction, the reactants are high, and as we use reactants, the concentration goes low. Eventually, the concentration of reactants and products starts to be stable and not changing. This is when we reach equilibrium. Notice that they are not the same, they are just unchanging. So that is one definition of equilibrium. So an example of an equilibrium here, just to show you what I mean, forward reaction, I mean the arrow on the top going forward. Reverse reaction, we mean the arrow going in reverse. And so at the same time that these molecules are reacting to make this molecule is reacting to make these molecules. So we don't see a change because as one goes to the other, another's coming back. And so the rate forward and reverse is the same, and the amount is unchanging. And so you can look at this graph kind of showing you the rate. So our first graph showed us the concentrations changing. So rate of the forward reaction starts high because I'm only going in the forward direction. And as I start to slow down in the forward direction, I start to speed up in the reverse direction. Eventually I get to a point where the rate forward and reverse are the same. That's what's equal at equilibrium. So just to come back here really quickly, concentration of reactants and products does not have to be the same. It just has to flatline. It has to stop. What's the same? The rate forward and reverse is the same. And talking about Le Chatelier's principle, this is a principle that says if you have a system in equilibrium, okay, it's in this groove, it's got this back and forth, this rate that's the same. If you mess with it, it will try to go back to the way that it was. And so you will have a shift toward reactants, toward the left, or a shift toward the products, toward the right, to compensate for whatever you've done to it. So we're looking at some ways we can stress our equilibrium. And so looking at this image, it kind of shows us that if we have equilibrium, the water levels are equal. They don't have to be equal at equilibrium, but in this example it is. If I were to add a whole bunch of water to tank A, it would eventually flow into tank B, and then I would get an equilibrium again. And so this is just kind of an example, not a great example because it makes you think reactants and products are the same at equilibrium, and they're not. But in this example they are. You can see that it will shift to maintain the way that it was before. If something is at equilibrium, that means that it just naturally fell into this stable condition. And when you mess with that, it's going to change back to the stable condition. And so looking here, what happens if I add nitrogen dioxide? If you add something, the equilibrium says, no, that's too much of this, so it uses it to make some of this. And so if you add something, we're going to shift away from that thing. And so I want you to remember add, away. If you add something, you're going to shift away from that thing. So if I add NO2, I shift to the left because that is away from the NO2. It's too much. And so I'm going to use some of it to make more of this so that it can balance out again. And so here's another kind of reaction showing you the same thing, just using the molecules. So what happens if I add N2O4, dinitrogen tetroxide? Well, it would shift away from the N2O4, which is to the right. And so here's an example kind of just showing you all the possibilities in an example. And so for you guys, remember that add, away. So add something, shift away. And then if you take something, you're going to shift toward that thing. So what happens when I take away something? Well, then the equilibrium says, well, I don't have enough of that anymore. So if I decrease H2, there's not enough H2. So I'm going to shift toward H2 to replenish it. So this is more of a replenishing effect. And so looking back at our hypoxia again, if your oxygen level is high, I will add oxygen and I'll shift away, making more oxyhemoglobin. If my oxygen is low, I will take, so shift toward the oxygen, making more regular hemoglobin and getting rid of the oxyhemoglobin that I need. You can experience hypoxia if you get up to 18,000 feet. So this is something that only when you're going into the very, very highest of the high. And here are some medical symptoms that people with hypoxia may feel from not having enough oxygen. A decrease in oxygen will shift us to the left, and that breaks down this oxyhemoglobin, which we need in our blood. That's how we transport oxygen to our cells. So let's do a quick check. So pause and do a learning check. Tell me if it's going to shift toward the products, right, or shift towards the reactants, left. Okay, so adding some carbonic acid. So if I add something, I'm going to shift away from that thing. So add, away. So where's the carbonic acid? The carbonic acid is here. And so if I add, I'm going to shift away from the carbonic acids to the right. So to the right, toward the products. If you remove something, that's like taking away. So take, toward. Where is the bicarbonate? The bicarbonate is on the right side. And so if I'm going to remove this, I need to replenish it. So I will shift right toward the products. And if I add some hydronium, if I add, I shift away. So if I'm adding the hydronium, I will shift left toward the reactants. And so now that I understand equilibrium systems, I can look at one really special equilibrium system, which is the equilibrium that water does with itself. So water is super weird. We've seen before it can act as an acid or a base, but it will actually act as an acid or a base with itself. So you'll get one water molecule donating a hydrogen ion to another water molecule, making its own conjugate acids and bases. And this is an equilibrium, so it's a weak thing that it does. It's not a lot. So we can think about it as an equilibrium system. This property, acting as an acid or base, makes water amphoteric. So amphoteric is the term used for something that can act both as an acid or a base. And you can label the conjugate acid-base pairs for this as well. So some math that we're going to use for this. For pure water, the concentration of hydroxide and hydronium is the same. And so I want you to know that if you see brackets, this means a concentration. And the unit is the molarity. So the concentration and molarity is what this brackets mean. And so it's just a shorthand for saying concentration. So the amount of hydronium, which is also the same as the amount of hydrogen ion, is equal to the amount of hydroxide when water is pure, and this number turns out to be 10 to the negative 7. Which means that if I have these two multiplied together, I get this constant. So this is a constant called the water dissociation constant. And so Kw is equal to hydronium concentration times hydroxide concentration, and at a certain temperature it is 10 to the negative 14. It doesn't have a unit, it is a constant. You have this on your periodic table, so you don't need to memorize it, but you do need to know how to use it, and we're going to look at this. So if you're in a neutral solution, your hydronium and hydroxide are the same, so pure water is neutral. But if you were to dissolve something in water and it wasn't exactly neutral, we could actually measure the hydronium or hydroxide concentration and figure out if it's more acidic or basic. So take a look at this example. If I add an acid to pure water, I add a whole bunch of hydronium, right? Because that's the definition of what an acid does. It donates that H+, so it's going to make more H3O+ when it donates it to water. So just as a reminder, an acid, just generic HA, reacts with water, and it makes hydronium and whatever A- is. So chloride, nitrate, whatever. But I'm making hydronium, so my hydronium goes up. If my hydronium goes up, because those two have to be equal, or they have to add up to 10 to the negative 14, my hydroxide has to go down. So now my hydronium is more than my hydroxide, which means my acid part is more than my base part, so my whole solution is acidic. And so I can remember that they need to multiply together to make that 10 to the negative 14. And so if one goes up, the other must go down in order to remain true. The opposite is true if you were to add a base. And so adding a base to water increases the OH. If you increase the OH, then you have to decrease the hydronium, so your base part is bigger than your acid part. Your whole solution is now basic. And so here's a summary slide of all of the different ways you can look at the hydronium hydroxide concentrations and figure out what kind of solution that you're in. And here's some numbers to show you. And so if I can look at these exponents and kind of think they should add up to about 14. If you have ones only, they should add up to exactly 14 or negative 14. But if you have numbers in front, then they will kind of add up to negative 15. So if we see here 5 and 10, 15, 11, and 15. But if there are ones in front, it should be exactly negative 14 that it adds up to. That's just an exponent rule. You can also just plug into your calculator as well to determine. Now, if your H3O+ is bigger than your OH, you're acidic. Now, you have to remember that negative 2 is bigger than negative 12. Think about a bank account. Which one would you rather have in your bank, negative 2 or negative 12? Negative 2 is better in my bank account, so it's more than negative 12. And if you're looking at like this basic one, negative 8, negative 6, which is more, negative 6 is more, because again, this is better in my bank account than negative 8. And so just comparing these is going to be really helpful in determining what type of solution we have. So go ahead and do a quick calculation and make sure you put it in your calculator correctly. Calculate the hydroxide for each of these hydroniums. Okay, so I will do this by looking, remember that this Kw, this water constant, is equal to hydronium times hydroxide, and this number is equal to 1 times 10 to the negative 14. And so if I'm trying to solve for hydroxide, currently hydroxide is being multiplied by hydronium, and so we need to divide both sides by hydronium to isolate the hydroxide. Again, I want you always to think about rearranging algebraically before you start plugging numbers in. It just makes everything a lot easier. So here's my formula that I'll need to use to solve for my wanted variable, which is the hydroxide. I want to calculate the hydroxide. And so now it's really easy for me just to say, okay, well, 1.0 times 10 to the negative 14 divided by each one of these numbers. And so this just becomes a very simple calculation that I can use. And I get 1.3 times 10 to the negative 10. And so going through this, you're going to do the same thing for all three just to get a feel for it and make sure you're putting it in your calculator correctly. If you have questions about how to put it in the calculator, please let me know sooner rather than later. So I get this 6.7 times 10 to the negative 6, and your concentration is in molarity. Here we're going to get 1.0 times 10 to the negative 7 molarity. That is your molar concentration of OH, so your hydroxide. So being very clear about what we have here. Sig figs here, the KW is infinite sig figs, so don't worry about that. For sig figs, you want to look at these. And so in front of your times 10 is always how many sig figs you count. These all have 2 sig figs, so our answers should all have 2 sig figs. So what can I do with this information? Well, I can actually calculate the pH. So what does it mean to have a high hydronium concentration? So high hydronium concentrations are going to be way down here. So 10 to the negative 1 is bigger than 10 to the negative 2. And these are going to be more acidic. If my hydronium is high, my hydroxide is low. And so 10 to the negative 13 is very small versus 10 to the negative 1. Again, my bank account, I'd rather have negative 1 than negative 13. So if your hydronium is greater than your hydroxide, you're acidic. In the opposite side, if your hydroxide is greater than your hydronium, then you're basic. But sometimes these numbers are hard for us to look at, and so we have another system of looking at the acidity. It's called the pH. So here's your pH scale. pH scale goes from 0, it goes from 0 all the way to 14. Your pH of 14 is very basic, your pH of 0 is very acidic, versus a pH of 7 is neutral. And so I want to highlight this 7 as neutral. pH of 14 and 0, those are your guidelines. So between 0 and 7, your pH is telling you that it's an acid. If you have a pH 7 to 14, it's a base. And so here's another slide showing you this greater than less than, and then your hydronium, if your pH is low, that means your hydronium is high. Because it's kind of the opposite, and we'll talk about what exactly pH is as far as doing the math. If your pH is exactly 7, it's because your hydronium is 10 to the negative 7. And so there's a relationship here between the exponent and the pH number. Because pH is a log base thing. So I'll give you this formula really quick. You can write it down. So pH is equal to the negative log of hydronium concentration. You do not need to understand logs. You just have to press the log button on the calculator and change the sign. And so you can actually look at the 10 to the negative 7. If you take the negative log of that, you should get 7. So go ahead and pause and give me an acid, base, or neutral based on these pH information. Well, if you have hydrochloric acid with a pH of 1.5, first of all, it's probably an acid because it's hydrochloric acid, but we can look at this pH 1.5. That is less than 7, so it is an acid. If your pancreatic fluid has a hydronium of 10 to the negative 8, now remember what I'm comparing is 10 to the negative 7. And so is this greater than or less than 10 to the negative 7? Well, 10 to the negative 8 is less than 10 to the negative 7, and so my hydronium is a little low, so it's going to be basic. So your hydronium is going to be lower than your hydroxide. You can actually figure out mathematically if you want to the hydroxide, but it will be greater than negative 8. For a Sprite soft drink, pH is a 3, which is less than 7, so this is acidic. pH equal to 7, this is your neutral solution. If your hydroxide is 10 to the negative 10, is that greater than or less than 10 to the negative 7, which is neutral? Now, 10 to the negative 10 is less than 10 to the negative 7, which means it is less than your opposite, which is your hydronium. So your hydronium is more, meaning it's acidic. If you have your hydronium 10 to the negative 12, 10 to the negative 12 is less than 10 to the negative 7, which means it's less than the OH concentration as well, and you would have a basic solution here. This is just a list of some pHs of common things you can take a look at to kind of get your bearings on what pH means. pH is talking about the concentration, not the strength. So you can have something that is very strong with a very neutral pH, or you can have something that's very weak with a very low pH, or a high pH. So strength, remember strength is talking about how well it breaks down, the dissociation. So how well does it, dissociation. So 100% would be strong. pH talks about the concentration of hydronium. And so it doesn't really have anything to do with how much it breaks down. It has to do with how much is there in the first place. So be careful thinking that low pH means that it's a strong acid. That's not necessarily true. Strong only has to do with how well it breaks down. And so, and just a look at an example here. So gastric juice has a pretty low pH of 1.6, and that's typically because it has a strong acid in it, hydrochloric acid. Yeah. But lemon juice is citric acid, and that's a weak acid, and their pHs are very similar. And so you can't always say that strength is directly proportional to pH. pH is a log-based scale, and so every time your pH moves, it's base 10 that moves. So kind of like the Richter scale for earthquakes, a pH of 2 is 10 times more acidic than a pH of 3, which is 10 times more acidic than a pH of 4. So as we go lower in our pH, we're getting 10 times more acidic. As we go higher in our pH, we're getting 10 times less acidic, or 10 times more basic. Just like a earthquake on a scale of 7 is 10 times more powerful than a scale of 6. So how would I do these pH calculations? And we're just going to plug this into our calculator. And so looking at this, go ahead and pause and see if you can plug in and see what you get. But looking at what I'm going to do here is find the pH is equal to the negative log of the hydronium. If I give you the hydronium, then we're going to find the pH. Then we're also going to do whether the solution is acidic or basic. So here, I'm going to say my pH is equal to the negative log of this number. So you're just going to find that information on your calculator, whatever calculator that you're using, and press the log button. And here you should get 3.74. Now we're going to talk about sig figs in just a second, but let's just get some numbers. And here the negative log of 7.2 times 10 to the negative 9. And I'm going to just plug this into the calculator, so don't get too fancy. 8.14. Now, which is acidic, which is basic? So option A is acidic because it is a pH of less than 7. Option B is basic because it is a pH of greater than 7. So less than 7, greater than 7 tells us the acidity or basicity of something. Now what about those sig figs? So the rule is this: the number of sig figs in your concentration is equal to the number of digits after decimal in your pH. So if you have 2 sig figs here, you're going to have 2 digits after the decimal. So essentially the number in front of the decimal, or whatever numbers are in front of the decimal for pH, don't count for sig figs. And so going back to this example, if you have 2 total sig figs here, I need 2 digits after the decimal here. Again, 2 total sig figs, 2 digits after the decimal. And that's your last sig fig rule you ever have to know. So go ahead and give me a pause, give me one more sig fig calculation, but you're going to use a different, so we're going to use the opposite of a log. So to get out of a log, we raise everything by base 10. So try plugging this into your calculator, see what you get. So to plug this into the calculator, you should see, okay, if I want the hydronium concentration, I need to do the opposite of log. The opposite of log is raise everything base 10. And so kind of deriving this, you have the pH is equal to the negative log of hydronium. Everything gets raised to base 10, and we bring that negative over. And so we cancel out the log by raising everything to base 10 because that is what log means. It's a base 10. So looking at this, I'm going to say 10 to the negative 4.80, and you're just going to find that on your calculator and plug it in. Again, I don't need you to deeply understand all of the complexities of log math. I just need you to plug stuff in. So look at my sig fig rule. So this I'm going to go a little backwards. So look at my digits after the decimal are 2, and so my sig figs I want to report are 2 total sig figs. So 10 to the negative 5. And you always get a unit for your concentration, but sig figs do not have a unit. And so here are just some pHs. You can see how the exponent correlates with the pH as long as there's nothing in front of the times 10. And you can also see how your hydroxide and your hydronium add up to negative 14 if there's nothing in front of the times 10. We have seen this before, but acids do a thing where they can dissolve metals and they make a salt. So a salt is an ionic compound. When I say salt, I don't always mean sodium chloride. And you will see that we kick out hydrogen. So this is a single replacement reaction. And hydrogen is getting kicked out. So you will see bubbles when you drop most metals into acid. There's some metals that the hydrogen won't get kicked out, like those ones in the very low part of your activity series. When an acid reacts with a carbonate or a bicarbonate, and you saw this reaction, it makes carbon dioxide and water. And then it makes an ionic compound. And so how would you initially see this? You initially see this as carbonic acid, is what you would initially see this, and it immediately decomposes into carbon dioxide and water. So when you do your double replacements, this is a double replacement, you see this carbonic acid being formed. And so looking at the carbonic acid, it's because of the switching of the ions that we see then. So if you need help with that double replacement math, or like switching those ions, let me know. But as soon as you see carbonic acid, you need to know automatically breaks down into CO2 gas and water liquid. When you put an acid and base together, it neutralizes. And so what are the most important parts of this neutralization? The H plus and the OH are what make the water. That's the neutralization that's important. Whatever is left over becomes the ionic compound, the salt. And so we say acids and bases react to make water and a salt. So the last part we're going to talk about is titrations. We're going to be doing a lab later next week, or later in the semester, where we titrate. A titration is a process where a substance of known concentration, so you know the molarity of one substance, and you don't know the molarity of another substance, and you're going to react it to decide and do some stoichiometry math and how to figure that out. So do some dimensional analysis, conversion factors. Your titration. We're going to be using a substance called phenolphthalein that turns pink in a basic solution, and we're going to drop it into this solution. And so you have a titration, you have an acid, so typically, and we're going to have this acid in the bottom, and we're going to have a base up here, and we're going to be dropping the base. When you drop the base, it reacts to make water. So here's our little water molecules, and eventually you get to a point where everything is all reacted into water, and one more hydroxide comes on down and changes the color of our phenolphthalein. And we'll be going more into detail with this as we do that lab. So here's some real pictures of that color change. But of course there's math in it, and so I'm going to show you how to do this. If you want to pause and give it a shot, you can. Remember, the molarity from the last chapter is a conversion factor, so we'll use that. But give it a try and see how far you get. Looking at this, first of all, I have a titration, which is a reaction. So anytime you see the word titration, you need to think, oh, this is a reaction. If you see that you're doing a reaction in math, you need to write an equation for that reaction. So we have HCl, which is an aqueous solution if it's an acid, requires how much sodium hydroxide? So sodium hydroxide is the base. And what do I make? Well, I have an H and OH to come together. That makes water. The state of matter for water is liquid, not aqueous. And then I have the salt, which is sodium chloride in this case. I'm just doing a double replacement math with my ions here. Now, let's just look at all the information we have about each thing. And so for the hydrochloric acid, I have a volume, but I don't know the molarity. And so I want to know the molarity of the HCl. And I'm given the volume. Oops. I'm given the volume and the molarity of the sodium hydroxide. And so one thing I have to remember though, if I'm changing substances, I need a mole ratio because I have two different substances. You cannot use the dilution equation as much as you want to here because it doesn't allow you to change substances. And Khan Academy does a really bad titration example where it uses the dilution equation. And yes, it works for that example, but it is not always going to work because your mole ratios are not always going to be 1 to 1. So I'm going to show you how to do it without using the M1V1. So please don't use that for any titration. You should use a mole ratio. So going through this, where do I want to end? I want to end at the hydrochloric acid, right? I want to end here. Whoops. I want to end with hydrochloric acid. And so I need to start with the other thing. And so we're going to start with the sodium hydroxide. And so I don't want to start with the molarity because the molarity, let's rewrite as a conversion factor. So I'll give us a little more space here. So the molarity is the mole of sodium hydroxide in how many liters? Right, in 1 liter of sodium hydroxide solution. And so rewriting the molarity like this can help me remember that it is a conversion factor. So in order to use that conversion factor, I need to be in liters. So one quick thing I can do is to change milliliters to liters, pop the decimal back 3 places. It's like dividing by 1,000. And so I can say, well, I know that 0.01254 liters of sodium hydroxide are being used here. So starting with that, 0.10124 liters of sodium hydroxide is going to be where I start. Don't start with the molarity because that's a conversion factor. And so now I know I can go to moles of sodium hydroxide, but I need to talk about moles of acid. And so looking here at my chemical reaction, I see that these are 1s in front. So I'll write 1 mole of sodium hydroxide is equal to 1 mole of hydrochloric acid. And I will use that as a conversion factor. Now, what am I trying to find? I'm trying to find the molarity. Molarity is equal to moles over liters. And if you look here very carefully, I have the liters of hydrochloric acid. So I'm really trying to find the moles. So I need to stop at moles of HCl. That's where I really want to stop. And so coming back here, we're going to start with our molarity of sodium hydroxide because it is 1 mole per liter. Now I have moles of sodium hydroxide. That's cool, but I want moles of HCl. So for every 1 mole of sodium hydroxide, I have 1 mole of hydrochloric acid. And that's what I said I needed, right? So let's stop here and actually get a quick mole answer. And you get 0.00124 mole of HCl. Now in order to find molarity, I need moles divided by liters. So what are my liters of hydrochloric acid? Well, if you do my trick again, 1, 2, 3, you get 0.01000 liters of HCl. And this will give us our final answer of 0.1254 molar HCl. And I want 3 sig figs here because of my molarity, so I will do 0.125 molar HCl. This is nothing new. We're just using molarity and mole ratio as conversion factors. Okay. So last little bit here, buffers. Buffers have 2 jobs, or two things about a buffer you need to know. First, Buffer contains weak acid and its conjugate base. So not any conjugate base, but the actual conjugate base that goes with that acid. And a buffer resists changes in pH. And so if you add an acid or a base to a buffer, it's not going to change its pH too much. So here, looking at your change, you start with 7.0. If you add an acid, it'll change its pH to be a little bit lower, like 6.9. If you add a base, it'll change its pH to be a little bit higher, like 7.1. But if you add an acid to water, it will go from 7 to 1, not just 6.9. And so you really get a very drastic difference between a buffer and pure water. So the buffer will change its pH a little bit, just not a lot. That's the job of buffer. You have a buffer in your blood that keeps your blood from becoming too acidic. And so here's how a buffer system works. You have a base. If you add a base to a buffer system, the base will react with whatever acid you have. So you're looking at a buffer, it's got two parts. It has an acid and it has a conjugate base. So when you add a base, the acid comes in to neutralize it. When you add an acid, the conjugate base of that acid comes in to neutralize it. Look at the acid, acetic acid. What is the conjugate base of acetic acid? Well, if you get rid of the H+, you get acetate. And isn't sodium acetate really sodium ions and acetate ions? And so sodium acetate is the conjugate base of acetic acid. It's just the one part of the acetate ion that's doing the reacting. So this acetate conjugate base reacts with the acid to neutralize it. And this acid reacts with the base to neutralize it. So here we can see this happening on a nice little diagram. So go ahead and pause and check to see which one of these is a buffer. Okay, so HCl and KCl. First of all, you need to ask yourself, is this a weak acid? So is this a weak acid? No, because HCl is a strong acid. So that can't be a buffer. So automatically no. What about B? So carbonic acid. Is carbonic acid a weak acid? Yeah, so that's a weak acid. Now I'm looking for the conjugate base for that weak acid. So let's take this weak acid and let's look for its conjugate base. The conjugate base, remove an H+, right? So we have HCO3-. That's bicarbonate. Is this bicarbonate? Yes. So this is a buffer because it has both pieces. Now let's look at C. Phosphoric acid. Is that a weak acid? Yeah, that's a weak acid. But is this the conjugate base of phosphoric acid? So looking at phosphoric acid, if you get rid of an H+, you get H2PO4 dihydrogen phosphate. So that's not, Cl- is not the conjugate base for phosphoric acid, so this is no. And then lastly, looking at this, acetic acid, is that weak? Yes. And then is potassium acetate the conjugate base that goes with it? So if you're looking at the conjugate base that goes with the acetic acid, you get acetate. And then potassium is just what the acetate is with at the moment. It does not, it's kind of just watching what's happening. So is the sodium here. So you'll notice that all your conjugate bases, they have to have some kind of plus, some kind of cation to go with them. You can't just have a negative by itself. So you can't just grab acetate off the shelf. And so here's just a slide for you to kind of give that same example in a little probably neater way than I just did.